When you use the integral test, you can determine whether or not a particular series converges or diverges based on an integral, but you can't use the integral to find the value of the series. In this video, we're going to explore ways that we can use integrals instead to estimate the value of a particular series. In order to understand how we can estimate the value of a series using integrals, let's look at this picture. We've seen this before for the integral test itself, or a similar picture. So let's recall that in this picture, the blue rectangles, the area of each of those is equivalent to one of the terms of our series. In particular, the first rectangle has an area of a sub 1, the second is a sub 2, and so on and so forth. Now, if we imagine this goes out to some arbitrary value n, then we can see that this rectangle right here is going to have the area of a sub n. If we look at the orange rectangles, the first rectangle is a sub 2, a sub 3, so on and so forth, and that means that this rectangle here is going to be a sub n plus 1, and so on and so forth. So what we're going to do is we're going to consider our series, the sum from k equals 1 to infinity of a sub k. We're going to split it into two parts. We're going to look at the sum from k equals 1 to n of a sub k. We know that as the nth partial sum, s sub n. And then we're going to look at the sum from k equals n plus 1 to infinity of a sub k, and we're going to call that r sub n, the remainder. If we look at our picture, we can see that r sub n is represented using the blue rectangles. It starts at this point and goes on forever. That is r sub n. If we look at it using the orange rectangles, we can see that this quantity here is r sub n. What does that tell us? Well, now we want to think about this in terms of the integral. So notice that using the orange description of r sub n, we see that r sub n is smaller than the integral starting at this value, which is the integral from n to infinity of f of x dx. If we use the blue representation of r sub n, then we see that the integral from n plus 1 to infinity of f of x dx is actually less than or equal to r sub n. So looking at this inequality on the left, we see that the pink area is bigger than the orange area when we start at n. But then switching to this inequality, we see that the pink area is smaller than the blue area when we start at n plus 1. How is this helpful to us? Well, let's combine these two inequalities into one string of inequalities that looks like the integral from n plus 1 to infinity of f of x is less than or equal to r sub n is less than or equal to the integral from n to infinity of f of x dx. Now we have to remember that the sum from k equals 1 to infinity of a sub k, we split that up into s sub n plus r sub n. So we can add s sub n, our nth partial sum, to all the terms in our inequality, and we get that s sub n plus the integral from n plus 1 to infinity of f of x is less than or equal to s sub n plus r sub n, which is less than or equal to s sub n plus the integral from n to infinity of f of x dx. In other words, we see that s sub n plus the integral from n plus 1 to infinity to f of x has to be less than or equal to our series. And this gives us a way to estimate the area and, in fact, find out what the upper and lower bounds for our area is. So we can consider this value. This is going to be our lower bound. And this value is going to be, that's a very crazy looking bracket, but you get my point, that is going to serve as an upper bound. So we have two formulas we can now use. We know that the remainder, r sub n, is always going to be less than or equal to the integral from n to infinity of f of x dx. We can use this to find values of n so that our remainder is less than or equal to some given value. We also know that s sub n plus the integral from n plus 1 to infinity of f of x dx is less than or equal to the value of our series, which is less than or equal to s sub n plus the integral from n to infinity of f of x dx. And we can use that to find upper and lower bounds for our series for any particular n value. Let's use these two ideas now to get an estimate on the error in the series, the sum from k equals 1 to infinity of 1 over k squared, one of our pure series, and also to get an upper and lower bound for that series. First, let's see if we can find an n value so that our remainder, the part we don't know, is less than or equal to 10 to the negative 3, or 1 over 1,000. So we know that r sub n has to be less than or equal to the integral from n to infinity of our corresponding function, so that's going to be 1 over x squared dx. We'll evaluate that integral. That is going to be the limit as b goes to infinity of the integral from n to b of 1 over x squared dx, which is then the limit as b goes to infinity of negative 1 over x from n to b, which is the limit as b goes to infinity of negative 1 over b plus 1 over n, which is just going to equal 1 over n. So now we know that r of n is less than or equal to 1 over n, which means that if we want that to be less than or equal to 1 over 1,000, we need to let n be 1,000. So we would have to take 1,000 terms of this sum in order to guarantee that the remainder is less than or equal to 10 to the negative third. Now, let's see if we can estimate our series, the sum from k equals 1 to infinity of 1 over k squared, using 50 terms. Now, we know we can compute s sub 50, and that would give us a 50-term estimate, but our technique here allows us to get an even better estimate, because we know that s sub 50 plus the integral from n plus 1 to infinity of our function 1 over x squared dx is less than or equal to this sum that we're looking for, which is less than or equal to s sub 50 plus the integral from n to infinity of 1 over x squared dx. And based on the work we just did, we know that the integral from n plus 1 to infinity of 1 over x squared is going to be 1 over n plus 1. So we now know that s sub 50 plus 1 over n plus 1 is less than or equal to the series we're attempting to estimate, which is going to be less than s 50 plus this integral is 1 over n. We need a calculator to get an estimate of s sub 50, but plugging that into a calculator shows us that this is about 1.62 5, 1, 3. And I put equals there. I'm rounding, so I'm going to change that to approximately, which means that what we see here is that 1.62513 plus 1/51 is less than or equal to the sum, which is going to be less than 1.62513 plus 1/50. And so this value on the left is going to give us 1.64474, and that's going to be less than our sum for our entire series, which is going to be less than or equal to 1.64513. So our original estimate was as low as 1.62513 if we just use 50 terms, but now we can see that it's between these two numbers. And so if we average those two numbers, we can get a really good estimate of this. So we're going to take 1.64513 and add that to 1.64474, and then divide that by 2 to get that our estimate, our sum, is approximately equal to 1.644935. We'll wrap up with a quick summary of what we've learned in this series estimation theorem. So if we have a series, the sum from n equals 1 to infinity of a sub n, and there's a function f of x that's real valued so that f of n is equal to each of the terms of that function, and we know that f is continuous, positive, and decreasing for x greater than or equal to 1, then we can conclude that the remainder left over after calculating the nth partial sum is less than or equal to the integral from n to infinity of f of x dx. And we can also determine a lower bound and upper bound using the fact that s sub n plus the integral from n plus 1 to infinity of the function must be less than or equal to the series, which must be less than or equal to s sub n plus the integral from n to infinity of our function.